Slides.
Yeah.
Yeah. Hello everyone, I'm Ajay, lecturer in the section of pavement engineering, and my pronouns are he, him. The topic of today's presentation is viscoelastic materials. We will start with the formative assessment first, then we will continue with the lecture. I'll give a small background about myself before diving into the topic. I did my undergrad in India and my PhD at Singapore. Then I worked as a postdoctoral researcher for 1 year, and for the past 1 year I've been here as a lecturer. And in addition to my teaching, I'm also involved in the diversity and inclusion committee at the university. This is the team over here. You would have noticed some progress flag at the university. This is the team which is working for it. And this is the one at Open Friday. Then, yeah, these are all my teaching interests, starting from Muir, of course, then pavement materials, pavement mechanics, then followed by DEI. I have a small YouTube channel. If you are interested in any of my teaching or research or service, you can have a look at it. Yeah, let's go to the formative assessment. These are all the questions which we are expecting that you could answer something. The output is like 5 minutes presentation. Please stick to your time. We have lot of content in the next lectures. Then, yeah, let's start with the group one. Yeah. Okay, now it's my turn. I'll start the lecture on the viscoelastic materials. At the end of this lecture, you will be able to understand the concepts of rheology in construction materials. You will be able to analyze the importance of rheology in bitumen selection and modeling. And finally, you will be able to explore a little bit on the recent advancements. So this is the contents for this presentation. We will start with the general viscoelastic materials, followed by bitumen-related applications. Have you learned anything about rheology in any of your previous lectures, or is this the first time you're hearing about this?
I've seen it, but I don't know what it means.
Yeah.
Okay, sure. Yeah, no problem. We will start with the very basics from rheology. So before that, these are the main references. The first one is textbook from Professor Nicolaitis, chapter 4, and the second one is from Haji Karimi and Nijat. We will continue using these textbooks in the next quarter as well. Yeah. So what is rheology? People say like it's also a Greek word. Rheology is a study, and rheo is the flow of any soft material. The soft material can be a fluid or a plastic or anything like that. Yeah. So they defined it as the science of deformation and flow of liquids and soft matter. So this one has two important concepts. One is the viscosity and the other one is the elasticity. Under elasticity, we all know the basic Hooke's law. Stress is proportional to strain, and in this, whenever we apply a load, stress is always stored. It's always, whenever we remove the stress, the thing is already back to the original state. Under the viscosity, we have the Newtonian fluids. So in the Newtonian fluids, whatever energy is there, it will always be dissipated. But it's not a binary thing. It's in the spectrum, like it varies from Newtonian to the Hooke's law. So our viscoelastic material always lies in the regime of this particular thing, and it can either be liquids or the solids. So in this lecture, we will start with the comparison between what is Newtonian and what is non-Newtonian fluids. Yeah. When we say something as Newtonian fluids, we should understand from the basics, like if you look at the figure on top right, you can see a fixed plate and the moving plate. You should try to understand what's the shear stress and the shear rate of this fluid motion. if you try to plot the shear stress versus shear rate, it should be linear. If it is linear, it's the Newtonian fluid. The slope is what we call it as viscosity. So viscosity will be constant for variation in shear rate. There are multiple examples, you can see it in your day-to-day life. It can be water, it can be milk, it can be oils or fruit juices. So this is how we get the viscosity for the Newtonian fluids. When we say something about non-Newtonian fluids, it's again like very simply, it's the curve is non-linear between shear stress and shear rate. It can be in two different forms. It can either be like this or like this. So which means the viscosity is not constant over the variation of shear rate. This is for Newtonian fluids. This is for non-Newtonian fluids. One curve we call it as shear thickening, and the another one we call it as shear thinning. If the viscosity is reducing, we call it as thickening. And there are multiple examples for non-Newtonian fluids. It can be the various polymers, plastics, bitumen, or blood, or any other suspensions or food materials like ketchup. There are many elements in many examples for this non-Newtonian fluids. And this is a very interesting part, the non-Newtonian part. So if you look at the Rheology Zoo, there is a website. It has a lot of interesting examples. You can have a look at it. It has like shear thinning, viscoelasticity, thickening, and the rod climbing. So this whole thing is like this will raise your curiosity for the fluid dynamics and all the CFD part. We will mainly focus on the viscoelasticity. So what is viscoelasticity? You can again have elastic part and the viscous part. I'll try to explain as slowly and simply as possible for this particular thing. Under the elasticity, whenever there is a load applied, when you remove the load, it will go back to its position within a fraction of a second or something. But in the viscous part, there will always be the energy dissipation. So it will take some time to recover back to its original state. Yeah. With respect to the applications in construction materials, there are various applications. We can talk about the paints or adhesives, bitumen, or plastics at certain temperatures. So when we call something as viscoelasticity, there are three important parameters. One is temperature, the second is time, and the third one is the rate of loading. So this one is the temperature effects. If you look at the x-axis, it's the temperature, and y-axis can be of any stiffness, so we call it as just response to load. It can vary from viscous domain to the fluid domain. When the temperature is low, it behaves in the elastic zone. If the temperature is very high, it behaves as a fluid, as a viscous material. So that's why the graph looks something like this. And the second one is the time. So imagine if you have adhesive or any kind of paints. If the temperature is high, you can pour it immediately. But if the temperature is low, you can still pour the material, but it will take longer period of time. Yeah. The third important parameter is the rate of loading. So imagine this is any kind of paint or bitumen. If it is bitumen, you cannot touch it. Imagine it's a paint. So you can apply the load slowly and you can deform the material. But if you try to hammer, if you try to do that, you cannot, the deformation is not as high as compared to the soft loading. Yes. Now we will talk about these are the three important parameters. We'll start with the high temperature effects of viscosity. So whatever liquids or gases we have, With respect to temperature, the viscosity will either increase or decrease. If it's a gas, it will increase. If it's a liquid, it will reduce. So how do we measure the viscosity of any fluid, like Newtonian fluid or a non-Newtonian fluid? There are a few commonly used tests, like one is the capillary viscometer. In this, there is a glass tube, something like this. In this, you will pour your liquid and you try to measure how much time it takes to rise to a certain level. Yeah, you have a fill line, something like this. You will fill your fluids over here, and on the other hand, you will maintain a vacuum. So then it will start increasing on one side. So based on this marks, how much time it takes, you find the viscosity. There are some calibrating things available. Yes, the second one is the most important one, which is the rotational viscometer. In this, you can change the temperature, you can vary the material, you can put the spindle inside and let the spindle rotate for a certain amount of time. Then you will be able to find out the viscosity of the particular material. Yeah, this is how it will look like. In this, you can either use, you can find whatever the viscosity for whatever fluids. Over here it's shown as oil. In this, yeah, you can vary the temperature, you can vary the time. Yeah. So how do you find the viscosity from this equipment? Again, viscosity, we know it's the ratio of shear stress over shear rate. Shear stress can be obtained using the torque. How much torque is required to find out to get the viscosity. So that's the equation. You can use it for finding the shear stress, which is torque over 2 pi RS square into L. All the other parameters you know except the torque. Once you know the torque, you can find the viscosity. Yeah. Now the viscosity over the frequency. You can vary the speed and you can find the viscosity. So if you try to plot this particular curve, when you increase the speed for most non-Newtonian fluids, the viscosity will reduce. And you can even try to find out the zero shear viscosity. What do you mean by zero shear viscosity? You cannot make the frequency as zero, but you can try to plot the figure based on the nearby results over the lower frequency range. And this is one of the important parameters for investigating the storage stability of material. You mix two different materials, whatever the additives you have, you can try to understand how it floats or it settles down. I will explain that in the next slide. And the final one is the infinite viscosity. After a certain frequency, the viscosity will remain constant for any further frequencies. Yeah. So what is this zero shear viscosity? How is this important? If you are given with two different materials, for which one fluid it's low zero shear viscosity, and the other one if you have like higher zero shear viscosity, the low one will settle down faster. Whereas the higher one, it will take more time to settle down. So in the pavement field, we are using the term as storage stability. If we see it in any other disciplines, people mainly use the zero shear viscosity term. You can refer to this particular link later. Yeah, that's all with respect to the general introduction for viscoelasticity. Now I'll dive into the bitumen topic. Yeah, so we know that I think you may know, now you know the little bit about the basic properties of bitumen. How it adheres, waterproofing, durability, temperature sensitivity, and of course it's the viscoelastic material. That's the important thing. Yeah. In fact, this is one of the oldest experiment people have been conducting in Australia. They were trying to understand the viscoelastic nature of bitumen like 100 years back. This experiment is still running on. They just kept the certain amount of bitumen in a flask, and they are just observing how many drops it has fallen. So if you have a bitumen like this, if you keep on like this for a few years, it will slowly fall. So how long does it take? Yeah, that's what they are observing for the past 100 years.
A lot.
Yeah. So in fact, in the recent years, it's the number of years for each drop is increasing. The bitumen is aging, so it will again take more time to fall. Yeah. So if everything goes wrong, if whatever the design we are doing, if everything is going in the wrong direction, or if the climate change happens, the road may melt in some time. This is what happened in Australia once, in Queensland. The road started melting because of higher temperature, and this is how it is. Yeah, to understand the pavement viscoelastic nature, we will start with the different distresses of flexible pavement. There are multiple types of road failures. It can be like a bleeding or block cracking, corrugations. There are multiple types. We will mainly focus on two different types. One is the rutting, and another one is the fatigue cracking. Rutting is the longitudinal deformation of pavement structure under the tire positions. This usually happens at the higher temperatures, or if the bitumen is soft, this is what will happen. Another type of failure is the fatigue cracking. This happens at the lower temperatures and again like repeated loading of tires. Yeah. As we seen earlier, bitumen of course is a viscoelastic material. It's affected by time, temperature, and the rate of loading. If you look at that right side small image, if the bitumen is soft, what will happen? If the bitumen is brittle, what will happen? If it is soft, it leads to rutting. If it is hard, it leads to cracking, thermal cracking, fatigue cracking. Yeah. So this again, like with respect to time, any bitumen will become hard. It will become more brittle because of aging and because of cooling as well. But with respect to moisture, the opposite thing happens. The hard bitumen will become like soft. If it is again getting heated, it will again become soft. Yeah. In the previous lecture, you would have seen something about the superpave grading, viscosity grading, or penetration grading. I'll start with the viscoelasticity is mainly in the superpave grading. So that's why I'm showing this particular thing. Here we have like around 4 different tests. The first one is RV is the rotational viscosity. TSR is dynamic shear rheometer. These two are the things which we are going to study in detail. And the remaining 2 experiments we will see it in the module A. Yeah. We have certain limits for each of these experiments. If it satisfies, it's good. If it is not satisfying, it will definitely lead to some kind of rutting or fatigue cracking. Yeah. Let's start with the viscometer. There are multiple types of equipments for finding the viscosity. If it's a pure bitumen or the base bitumen, or if it is like bitumen emulsions, there are different viscometers. We can make use of it and try to find out what's the bitumen viscosity, of course. Yeah, I'll start with finding the viscosity. Let's start with viscosity variation over temperature. So with respect to temperature, increase the temperature, what will happen? Will it increase or decrease? Decrease, yes. If it is like this. So at the higher temperatures, something like this, it will be soft, so it will lead to rutting. At the lower temperatures, bitumen is hard, it will lead to fatigue. So we have to choose a particular range in which the viscosity is in a particular range. It will be safe to go for the field construction. Now, yeah, imagine we have 3 different curves. Which one is soft and which one is hard binder? This one. maybe if we take it as A, B, and C. So which bitumen was soft and which one is hard? A is soft, yes, right. So the soft one, which should be used in a hot climate zone or the cold climatic conditions? Yes, right. So the soft one should be used in cold and the hard one should be in hot zones. Yes. Now you have a bitumen like this. You're given a choice of two bitumens in which the viscosity at a particular temperature is same. Which one will you use in climatic in a zone where the climate change will happen or the width is high? Yes, you should use A. So this is again based on the climate change conditions. If you design a road using B, and in the later stage, if it's due to the climate change, it's again the temperature is varying. Some of the roads may melt, some of the roads may lead to fatigue cracking as well. So we should be careful with the choice of bitumen. Yeah. In addition to that, we can again make use of this viscosity for two important procedures. One is the mixing with aggregates, and another one is the compaction. So, yeah, during the field construction process. We have a particular limit for viscosity. Based on this, we will choose the mixing and compaction temperatures. Yeah. If you have, for example, this is a crumb rubber modified bitumen. Here the x-axis is the temperature and y-axis is the viscosity. The black line is the base bitumen. If you add crumb rubber to it, the viscosity may increase up to like 6 times. So for this, the temperature should also be changed. Mixing and compaction temperatures, if it is around like 130 and 150, you should increase it to 150 or 160, 170 probably. Again, the size of the crumb rubber also matters. If the size is small or high, again the results will be different. Yeah. How do you understand something about the viscosity? Now we'll move on to the next experiment, which is the rheology. So far everything okay, right? Yeah, perfect. We'll start with the dynamic shear rheology. In this, you will have a small piece of bitumen, almost like the size of a euro coin. You will try, there will be a fixed plate and there is a moving rotating plate. So you will keep the bitumen in between and try to shear the sample. Once you try to do that, you will be able to get some shear stress or shear rate out of the sample. This equipment will try to find the torque required for specific displacement. Once you have the torque, you can find the shear stress, then you can find the viscosity as well, or there is a new parameter which we will discuss in the next slides. Yeah, there are multiple experiments. We will start with the rutting and fatigue factors at this point of time. But all these three plus we will discuss more in detail in the module A. Yeah. So to try to find out the shear stress and shear rate, we will try to get something from the engineering mechanics concepts. So where does the highest maximum shear happens, maximum shear stress happens, or the shear strain happens. If you look at the top view of this small sample, maximum shear stress will always occur on the edges. So here the T is torque or the radius, and down to 0 is the maximum shear stress. For the shear strain, if you look at this, we need to find the gamma. The equipment is capable enough to find this gamma as well. Here in this particular test, we can make it either as a stress-based test or strain-based test. You can either define the deflection and try to get the torque required, or give the torque as input and try to find the strain as the output. From the mechanics concepts, you will be able to get the shear stress and the shear strain. Mainly, you are measuring the torque from the equipment. Yeah. Yes. Now, So in this first one, we will start with the stress-based test. So if you look at the sample, you can see in the B figure, you can see the points A, B, and C. So first the spindle, it will go from A to C, then it will go to A, and finally come back to B. So that's why the figure looks like a sine graph. Yeah. So with respect to this, you can find the maximum shear stress, tau max. Give this as input and try to get the strain. Something like this. When you say something like when the material is purely elastic, the result there won't be any kind of phase lag. So the delta over there would be 0. That's for the pure elastic material. You apply a load, there will be an immediate response if you take it back. If it is like a purely viscous material, there will be like a 90-degree deviation. Imagine this one is the one sine degree, this one is 360 degree. So this is 190, this is 90. So there is if it's a purely viscous material, there is 90-degree gap. So whatever the viscoelastic material, it will again lie in this particular zone from 0 to 90. That's the viscoelastic material. And once you have the results from shear strain, you can find out what's the maximum shear strain. So once you have the shear strain and shear stress, maximum shear strain and maximum shear stress, you can find G star, which is what we call it as complex modulus. And delta T is the time lag. We can find the degree in terms of degree, which we call it as gamma. So there is two parameters. One is the rutting parameter and the other one is the fatigue parameter. Rutting parameter is G star by sine delta and fatigue is G star into sine delta. So people did some kind of correlations between the laboratory DSR based testing and the field performance. Based on the correlations, they found the G star by sine delta is replicating something of the rutting. Yeah. Once you have this, look at the figure 19, you can find more parameters, something like loss modulus or the storage modulus. Whatever the complex modulus, it's a complex number, so you can get the G dash and G double dash. Figure 18 is same as the elastic, viscous and viscoelastic thing. Figure 19, you can find the loss and storage modulus. Storage modulus is showing the elasticity, and the loss modulus is showing the viscous nature of the material. Yeah, that's all with respect to getting some results out of DSR. If you mix any kind of additives or modifiers to your bitumen, how does the microstructure will change? If you have some kind of polymers, it will stretch. It will again, like based on this, you can choose whether that particular additive or modifier is good for your. It's good based on the rutting and fatigue parameters. Something like this it may happen for different modifiers. Yeah. Now let's do a small problem solving. Nice. Yeah. Please. Okay. Sure.
I copy.
So in this, you are given with the dynamic shear rheometer test results. Here you are given with the stress and strain results. You need to calculate the complex modulus, phase angle, and fatigue parameters. let's have a time for maybe for 5 minutes time. If you don't understand the question, please feel free to ask me. Yes.
Could you go back a few slides? Yeah, I think.
Yes. Oh, for the equations?
Yeah.
Okay, sure. Here the easy part is finding the complex modulus. For the phase angle, I will explain later. Yeah. Here the tricky part is the phase angle. I can help you a little bit now. Yeah. So for the phase angle, we can simplify this figure like one is the stress and another one is strain. Here this particular thing is 0.2 seconds. For one curve it takes almost like 2 seconds. So if it's like for 360 degree, it takes 2 seconds. For 0.2 seconds, what's the phase angle? What is this part? If this whole thing is 360, how much is the degree? 36, right. So you can find it by 362 plus will come by 0.2. So delta is 36 degree. So once you have this 36 degree, you can find the remaining cutting parameters and other parameters. Yeah. So because of time limitation, I'll just quickly go to the next slides. Yeah, these are all the some of the answers. Yeah. So why do we need to characterize this particular thing? Why do we need to use this rheometer or the viscometer? We had seen it in the previous lectures. Of course, it's aging, polymer modification to evaluate the temperature sensitivity of different bitumen, and some of the other factors as well. Okay, how do we actually predict the distresses, payment distresses? If you look at this figure, x-axis is the size of the sample, and y-axis is the time required to get some results of properties. If you look at the larger scale, you need a very large quantity of samples. You will take more time to get some results of profit. If you are given with hundreds of different modifier additive sizes, crumb rubber sizes, different percentages, how do we choose one particular combination, and which will be the best in the field? For that, we are going to the lower scales. At this particular class, we were evaluating the binder performance. Then we will try to correlate with the field characteristics. We can again do the same with respect to the microstructure. We can find the exact microstructure and correspondent to the field performance. We can change the microstructure as well. Yeah, this is with respect to the experiments. Slightly I will introduce for the modeling as well. Why do we need to use viscoelasticity in pavement modeling? This is the finite element modeling for tire loading on the flexible pavements. If you use the elastic properties, what will happen? You use the viscoelastic properties, what will happen? These results are actually taken from the journal which I have shown below. If you use the elastic properties, pavement will again come back to its original state and the lifetime is very high. It's not the actual representation of the field. So that's why you can find, like, here the x-axis is the different road sections and y-axis is the cracking percentage of the different roads. So you can clearly see, like, if you use a viscoelastic material, it will again the cracking or the rutting or whatever the distresses, it will be higher. So we should always use the viscoelastic properties in the pavement modeling as well. Yeah. I think that's all with respect to this class. What did you learn so far what do you think are the highlights of this small lecture?
Maybe about the way that viscosity values are made up, so we experiment with.
Yeah. You need to understand it's a temperature sensitive material.
Yeah.
It's affected by time, temperature, and frequency. And importance of rheology.
How it affects the application for
Yes. How we can make use of this rheology in the final material selection or modeling, maybe. Yes. That's all with respect to this lecture. If you are interested in doing some MSc thesis projects, we have some topics available. Or if you want to create a new topic, you are most welcome. If you want to do something regarding the little bit of nude on pavement materials or modeling, or if you are interested in the environmental impacts of different pavement materials, like during the fumes, during road construction, or leaching during the service life, you can contact us. And yes, please feel free to provide some honest feedback. This is the first time we are running this lecture, so whatever the feedback you can provide us. It's anonymous, so don't worry, we can't trace you back. You can say, like, am I speaking fast or slow, or is there any story it's going well or not?
I didn't have a nice form, so give feedback for me also here. I will still use form now. I'm more traditional. I was like, send me an email, But yeah, use his form and write C did this and he did that. So.
Or if you want to see more kind of like example problems or whatever you can think of. Thank you.
Thank you, guys. We will be seeing you. Don't forget to send me your presentations, names and reference, and send it to me. I will upload them, so you have everything there. And okay, we'll see each other most probably in the exam or before. If you have any question for anything, as we said, and for specific topics that we teach as well, feel free to come. And we'll see each other in Module A soon.
Yeah. In A2, we will talk about the non-linear viscoelasticity. Just now.
Yeah, we'll do some tests, some
Yeah.
modeling. It will be nice.
Okay.
Okay. Great. Have a
Thank
good
you.
evening. What time is it? Yeah. Almost.
Can you just show the answers to the
Sure. I think I have only partial
You will
answers.
upload it also?
Yeah, I will include the slide as well.
Yeah. Include this as well.
Yeah.
Yeah.
Yeah. Yeah, if you want to look at the bitumen, this is how it looks. You can you can feel it.
Yeah. The idea is that you will work a bit with bitumen
Yeah.
in a
How long you were taking for the job?
If you keep it, it will take at least 12 years.
Yeah, not mix, because we are still going to evaluate the bitumen.
But if you increase the
level.
temperature,
Now we are
if you increase the
feeling
temperature, you can do it.
plus fever, so you will make a mix
Maybe some-
more on the low side, on your own. This is the idea.
Okay.
This is what we are trying
So
to set
what's
up.
CC,
Yeah, so
the
we
melting
make
point
small
or-
samples, small
that's the
specimens,
presentation
test
values
the
for
kids
this.
are,
Yeah.
most probably next year. I will see we are still, we have